Bueno, muy buenas tardes para todos. Leo, ¿nos escuchas?
Hola, sí, escucho. Buenas tardes.
Bueno, Leo, bienvenido a esta charla. Muchas gracias por tu participación. Hoy tenemos como invitado a Leo Dürst. Leo es ingeniero ambiental de la Universidad Politécnica Federal de Lausanne y está iniciando su maestría en ingeniería ambiental en la misma universidad. Entonces, Leo nos va a hablar hoy sobre Python y aplicaciones de Python en ingeniería ambiental y especialmente en calidad del aire. Entonces, Leo, bienvenido y adelante, por favor.
Bueno, muchas gracias. Gracias, Luis Carlos, de invitarme. Creo que voy a hablar en inglés porque es más fácil para mí, pero si tienen preguntas en español o si no me entienden, que me dicen.
Ok,
Entonces, sí, entonces voy a compartir I will share my screen now.
ok, go ahead.
Okay, thank you. 2 seconds. Mm, okay, can you see my screen?
Yeah, that's right. It's perfect.
All right. So, as Luis Carlos said, I will today talk about Amazon wildfires and a project that I was part of with him and with a group project from Sergio Arboleda. And together we worked on wildfires, trying to understand how they work. And I was part of analyzing numerically some data. So I'll show you what we did. But first, I'll introduce a bit problematics about the Amazon rainforest and how we worked around this subject. So to start, before talking about wildfires, I'll talk a bit about deforestation because this is just like a general introduction. But as we all know, the Amazon rainforest is losing a lot of area. As we can see, compared to its initial state, it already lost 80% of, no, it lost 20% of its surface. I'm sorry, there's a mistake, and 80% is remaining, which is quite a lot. As you can see, the orange curve shows that we're losing 0.3% per year of surface. And this is quite important because the Amazon rainforest is a really important ecosystem in our planet, and it has a lot of responsibility in regulating the carbon cycles, as well as it's a big place for biodiversity. And as we can see, the main drivers of deforestation are clearing for pasture to raise cattle and also to grow soya to feed these cattle, also farming, and then comes wildfires. So wildfires is not the most important cause of deforestation, but it is important, and there are reasons to think that all the causes are related to each other. So we will now study a bit further wildfires, and especially wildfires in the Amazon. So to start with wildfires, and especially for this research, it's important to understand that the Amazon is separated between a lot of countries in South America, 9 if I am not mistaken. And in these countries, different policies apply, and so we can imagine that the wildfires are not the same in every country. Some countries might have more wildfires, some other less, and the Amazon is different in each country. So we have to understand that each country will operate differently considering wildfires. But on average, on the graphic that you can see on the upper left part of the image, you can see that on average 15 megatons of CO2 are emitted from Amazon wildfires, which is really a lot, and it's important emissions. This only from wildfires. And some countries have been seeing their CO2 emissions from wildfires increasing over the last 10 to 15 years. These countries are, for example, Colombia and Amazon, or Brazil, that have had increasing emissions. And it's pretty important because for Brazil, in the case of Brazil, as it's the country with the biggest surface area of Amazon rainforest, if the fires and the emissions of CO2 are increasing, it means that a lot of surface is lost due to wildfires, so it's concerning. Colombia also has a curve that is going up. So as you can see, Colombia has been lately, in the last 15 years, maybe having more wildfires, so it's important. But on the other side, other countries have seen their wildfires emissions decrease, such as French Guiana, Suriname. A lot of countries actually have seen them decrease. But of course, these are trends, and it doesn't mean that every year the emissions will be lower. It just means that for the 15 years it has been decreasing. And it's interesting to see that things are not only going to the worse, emissions have been decreasing. And we can be happy for that and try to understand how it works and why some countries manage to see their emissions reduce, whereas some others only seem to increase. And we can also ask ourselves, what are the causes of such wildfires and how do we counteract them? And we will come later to this part, but as you can see on the graphics, there are some peaks that seem to go up quite a lot. For example, in 2010, this is like the third bar, it's going up quite a lot. And this maybe means that this year was special, and because it goes up in almost every country. Then there is another year in 2016 that also goes up quite a lot. So you can keep that in mind, and maybe we will understand why it's going up in these years and do some analysis about it. And do we have to worry about these peaks? Is it maybe due to a drought, maybe due to political actions? That's maybe the point of the research. Then, now let me introduce you a bit of the political responsibility in wildfires. On the graphic that is here, it's not showing actually wildfires, it's showing deforestation in general, but we can imagine that wildfires are also concerned by this graphic. And it's interesting, I thought it was interesting because it's showing deforestation in Brazil since 2002, and it's showing that from the early 2000 until 2010, the deforestation in Brazil was decreasing a lot, going from almost 30,000 square kilometers deforested in 2004 to less than 5,000 square kilometers, so almost a ratio of minus divided by 6, which is huge. And then we see an increase from 2012 to 2013. And under you can see that the presidents that were ruling Brazil were not the same in these periods. So we can think, are wildfires related to politicians, to politics, to political actions that are taken? And if so, well, it has some big consequences on the Amazon rainforest. And maybe it's interesting to see how these political actions can have an impact on wildfires and try to choose wisely our politicians. So these are a few questions that I stated on the right. What is the responsibility of politics in wildfires, if they have some responsibility? What are the actions that can make a real change in the fight against wildfires? Maybe we can see that some actions we think they're beneficial for wildfires in the Amazon and they're reducing them, but maybe it's not the case analytically, so it's interesting to compare them. Are some areas more vulnerable to wildfires? That's also important because some areas might be more vulnerable and also richer in terms of biodiversity or of indigenous communities, and maybe it's even more important to preserve them than others. And finally, are some areas more strategic in climate change fight and ecosystem preservation? Because as we know, a forest is a system, and maybe some areas are like the heart of the system and need to be preserved even more because they are more effective in terms of climate change regulation and forest regulation in general. So these are a few questions. Now, after politics, let's talk about climate for a bit, because there is, of course, a high chance that climate will be involved when we talk about wildfires. And the little image that you can see on the right shows it pretty clearly that if temperatures are rising, of course, it will be drier in forests, which means that there will be more wildfires, which will increase CO2 in the atmosphere, make it drier around, and increase wildfires. So temperatures are definitely a parameter in wildfires that we will analyze further. And more than temperatures and climate in general, we can talk about the general climate change, which is a really important topic right now, and how it will be influencing and affecting wildfires in the Amazon. And there are not only temperatures, but maybe some other parameters might be impacting wildfires, such as winds, such as precipitations, such as leaf vegetations and vegetation cover. So we can also try to study these parameters analytically and try to see who is responsible and what parameter is responsible for what cause. Another question that I stated was, what areas are the most vulnerable to climate change in terms of wildfires? And as of before, some areas were really vulnerable to political actions, maybe in terms of wildfires. Well, maybe some areas are also very vulnerable to climate change in terms of wildfires. So we have to study both cases. And finally, and most maybe interesting for us, is, can we actually predict wildfires in the future? Can we understand where they start, how they start, why they start, and make models to predict it? This is a bit of the work of the environmental scientists with his programations to try to model the climate or maybe the wildfires and try to understand how they will appear in the future to take the best decisions. Related to what we said before and the peaks I showed you before in the carbon emissions, I don't know if you remember, but an interesting thing that we will also maybe analyze are more general trends in climate, because climate is a complex system with very unpredictable events, but there are also some phenomena that will repeat over the years and that we're studying very hardly to understand how they work and what are the consequences on forests, for example, and on wildfires. And one really famous phenomena that you probably all know is, of course, El Niño, La Niña, that happen in the Pacific Ocean and in the southern hemisphere between Australia and South America, and South American coast, let's say. And basically, it's like a phenomenon that will see temperature increase due to a move of currents in the Pacific Sea, and it will highly impact precipitation regime in the countries bordering El Niño or La Niña, and it will also highly impact temperatures. And for this reason, we know that there is a pattern, and that El Niño, La Niña, that is kind of the both sides of a coin that we flip. El Niño is like we would say the warmer event in South America, and La Niña is the opposite, is the colder event, but of course that is not so simple. And well, if we know that such a phenomena exists, then we can already see some kind of patterns in the climate and try to relate it maybe to our data and try to see how wildfires are influenced. So if you take a quick look at the graphs, you can see that, for example, in 2016, that is shown here, I don't know if you can see my mouse. In 2015, there was a really, really strong El Nino event. And this is the same year that we saw a big increase in wildfires and in CO2 emissions in the graphs that I was showing you before. So it's already interesting. In 98 as well, a really strong event. So let's move on now. Now I'll talk a bit about the research that was initiated by Luis Carlos and the idea behind it and where what we want to do about these ideas. So the idea of the research is to try to compare meteorological data and causes to the wildfires to political actions. So I don't know if I was clear, but what it means is that we know that the politics have responsibilities in terms of wildfires, and we also know that the climate has responsibilities in terms of wildfires. If it's hot, then there are more fires, maybe. And if a president such as Bolsonaro is president of Brazil, maybe he will take actions that will encourage wildfires. And what is now the research about is to try to make the part of the responsibility of each group. If there is a wildfire, what is the response? What is the what was caused by meteorological parameters such as temperatures or winds, and what was caused by political actions. Of course, it's not as simple as that. You cannot say that a wildfire was caused half by a political action and half by high temperatures. But if we do concrete research, we can try to find patterns and, as I said before, understand what is happening and take correct political actions to counteract wildfires. So this is basically what the research is about. And the goals of the research, eventually, if they end up and if we manage, would be to try to determine the responsibility of human-induced versus naturally caused wildfires. And to do that, we have to analyze the trends in countries and see why countries have different profiles and some not, and try to understand these patterns. Then we want to understand what impact political actions have on wildfires in the Amazon. And finally, the goal of this research is at the end to, if we understand it well enough, to spread the word, sensibilize on climate change and wildfires and how they work. So this is a bit of the scope of this research. And for this reason, the research was separated in two groups. The first group is the politic group, and the other group is the meteorology group, or the numerical analysis group, if we can call it like that. And I was myself part of the meteorological group, more the numerical part, the analysis of the data. And there were other people working on the political side. And what each group was doing was that for the political group, for example, they were doing in-depth analysis of environmental policies in selected countries, which means that for these countries, they were going through the regulations, the policies, going through the the history of wildfires in these countries and the regulations, and try to see how each country were reacting to wildfires. And they were doing this in a comparative way to see differences between countries and see the context of each country as well. And it's pretty interesting because, for example, in Ecuador, we know that wildfires, if I remember well, are caused by, there is a lot of deforestation due to cattle, which can bring to wildfires. But in some other countries, such as Colombia, it's slightly different. There are other aspects to consider, and it's another situation. And all this was done also by researching in the existing literature and try to understand the scope. On the other side, the meteorological group, which I was part of, was had the goal of doing a numerical analysis on the climate in selected countries as well, in the same countries, of course, to then try to compare. And these numerical analyses were done with data, which we took from Copernicus. And so Copernicus is really nice because it's a big database that is free to use. It's there's no fee. It's open for everybody, and it has a lot of data. And Copernicus is the agency, the European Agency for Atmospheric and Climate Research, something like that. And so basically they have a lot of data, and they make it open to public for any researcher, any investigator to research and find what they will find. So all informations about the world, the atmosphere, the climate is there. It's a bit like the NASA, if you want, or the NOAA in the US. And we used this database to do this research. And then we did some in-depth studies of climate behavior and try to compare models between countries. It's always the same. It's always comparing, analyzing, using statistical tools, try to see which parameter is responsible for what. So this is basically the numerical analysis way of working. And of course, these two groups had to get together to compare results, to think and keep searching and try to get more precise on what we were looking for and get the best method. So now we can finally, after this long introduction, I'm sorry for the time I took, but we can finally start properly our lesson. And we can start coding and start finally to see how we went to go through this data. As I showed you before, we used Copernicus, the database. And then to code, I used extensively Python. That is a really nice coding language that you know already, I think, with the library xarray, which is powerful to deal with database and variables that can handle a lot of data. So this is really common in data analysis. So first, we had to download data. As I told you, it was from Copernicus, and there are two main databases. That is the Climate Store, which is called CDS, and the Atmosphere Store, which is called ADS. And from these two databases, you can basically access them freely on internet. You have to do an account, and then you can use their free tool that is an API that basically makes you do requests to request the data, and you can download them on your own server or computer. But you have to be careful because these data are quite heavy. There are a lot of things in there, so you have to select what you want and not download everything, otherwise it will not work. I'm saying it because I experienced it. It was a bit hard. And as I said, all data is free and open to use, so that's amazing. And on the right, we'll go through it a bit more after, but there is the simple code. As you can see, it's really simple, and it's the code that will make you download your data. And by changing the parameters, you can choose what you will want to download, with what frame of time, the months, you can choose the months, the days, you can choose basically everything. There are a lot of options and a lot of databases, so it's amazing. There are about everything, every kind of database. There are about atmosphere, about soils, temperatures, humidity, pressure, a lot of things about the Earth. And now I will tell you more about the data that I downloaded and that I analyzed. So in the group, we decided to focus on 4 countries, which are Brazil, Colombia, Ecuador, and French Guiana. And we chose these 4 countries because looking at the graphs that I showed at the very beginning with the CO2 emissions, there were countries that seemed to be interesting in terms of wildfires evolutions in the last 15 years. And for example, Brazil and Colombia were both countries that were seeing their wildfires emissions increasing, whereas French Guiana had a clear decrease and Ecuador a slight decrease. So we thought it's interesting to study these 4 countries because, well, we could have studied all the countries involved in the Amazon rainforest, but maybe one day we will do it. It's a bit of work, and we chose to just focus on these 4. And the data that I downloaded had all these parameters that you can see. So we have wind speed, temperature, precipitation, dew point temperature, soil moisture, plant coverage, fire emissions, and more. And you can download way more. And we chose also to focus on these parameters because with our knowledge of the matter, we thought that they were the most important to study, but of course, maybe it would be interesting to add parameters to study and to detail. So these are the data that I downloaded. And now with this data, we can do some beautiful graphs and we can have beautiful representation of the location that we study. After, I'll go through the code and you will understand every part of it. But if we look at it quickly, we can see that with this data, the data is constructed in terms of coordinates in space and also in terms of time. So if we take in Brazil, in the data set from Brazil, the wind speed in the U direction at 10-meter height, in at the 1st of January 2003 and we want to plot it, we can see what it looks like, and you can see the wind speed at every point in Brazil in color. I also chose to show you volumetric soil water in North and South America at the same date, and the graph is pretty nice. You can see that in the Amazon rainforest it's much drier, but we can also see a bit of mountain range that is the Andes, and that is a bit drier. But in the Amazon, sorry, it's more wet, I wanted to say. And finally, the last graph shows again the Brazilian map, but this time we chose to cut to only represent the Amazon rainforest and not the entire surface of Brazil. So to get a clearer focus on the Amazon rainforest and forget the rest, because at the end we're just focusing on the Amazon rainforest. And this graph shows surface temperature. So we can see that some places are much warmer and some are much colder in the Amazon rainforest. So these are all parameters that we will use in our analysis. Now, what I did was that I took all these data that were downloaded from 2003 to 2021, so 18 years, and we chose to try to compare fire emissions in countries to any other parameter and see if we could see patterns and trends. So I'll explain you these graphs because they're really important and they were the core basis of the research. You can see that we have three graphs. We have yearly, seasonally, and monthly. So it means that each graph show different time precision. And the yearly graph will show the evolution of a parameter to CO2 emissions for each year. So each year we averaged on every point in one country's Amazon rainforest, let's say the temperature, we average the temperature for the whole year in the whole surface, and we get a point. And then the next year we do the same, etc. And this gives us curves that give the average temperature for each year. And then we also plotted the tendency that show how's the trend going. So here we can see Colombia. The three graphs are for Colombia. And we see that I compared temperatures with fire emissions. And so you can see that that temperatures are going up from 2008 to 2021. And also fire emissions are going up. This is the blue curve. And now we want to see if there is maybe some link between the two. Are temperatures related to fire emissions? So we can calculate the correlation and we can calculate the p-value. So the correlations for the yearly curve gives us 0.4, which means that there is a 0.4 correlation, which shows us something, but is not significant enough. So on a year-by-year basis, we cannot say that over the whole year temperature is correlated to fire emissions. But now, if we go to the other graphs and we check, for example, we look at the season or monthly graph, again, we averaged the value for every point in Colombian Amazon rainforest, and we averaged temperatures seasonally or monthly. And now we get much more interesting curves because we have proper patterns of ups and downs. And we see that, for example, and this for Colombia, I think that in October and November, if I'm not mistaken, temperatures are higher in Colombia. Maybe I'm wrong, but I think these were the months. But also we have much higher fire emissions, and it's really correlated. We can see both curves following each other, and it's interesting because we clearly see that there is a trend between temperatures and fire emissions. And exactly in the lower side of the graph, you can see this trend by season. So there are just 4 points, and for the monthly graphs, there are 12 points, which represent the month. So I was actually wrong. The temperatures are higher at the beginning of the year in February and it's also when there is the highest peak of fire emissions. So in February and January, there is a lot of fire emissions, and there is also high temperatures, and you can see these trends averaged over all the years by month and by season. And now we get more interesting results in terms of statistics, because our correlations increase, and we see correlations of 0.77. So it's already pretty significant, and it means that there is a proper link between fire emissions and temperature. So we did this analysis for every country, for every parameter that we analyzed, and we did it yearly, seasonally, and monthly. And then we gathered the correlation and the p-value to see the value of our statistical analysis and what we could do with it. And this is a summary of it. I just showed the parameters for three parameters: temperature, precipitation, and relative humidity. And all these parameters are in comparison to fire emissions. So temperatures are highly correlated to fire emissions in every country. Precipitations are highly decorrelated to fire emissions in every country, as expected. If it rains more, there is less wildfires. And finally, relative humidity is highly decorrelated to fire emissions. And of course, humidity is correlated to precipitations in some ways. So it makes sense that these two parameters are decorrelated in the same way. And you can observe the correlation and the p-value for each of the results. Now, before going to the next slide, we have a overall view of the situation for each country and for each parameter, but we want to see if the parameters are maybe related to each other, and we're going to a next step, that is doing a multivariable analysis, and this is what I will show you right now. We do a multivariable analysis of all the parameters, including fire emissions, and to do this, we use tools of linear regression, and we use the library called sklearn. And it's a really powerful library to both do machine learning and also do multivariable analysis and deal with a lot of data. So I recommend learning about it because it's really good. And here I put two examples, and you can see if you take a square, if the square is red, it means that the two parameters that it's analyzing are highly correlated. So for example, for Brazil, there is a really red square between relative humidity and SWVL1, that is the soil moisture. So there is a high correlation between humidity and soil moisture, which makes sense. And like this, with these grids, you can make good analysis of which parameters are correlated to which. And for Brazil, you can see that fire emissions are correlated with temperatures, but uncorrelated with the soil moisture, humidity, and temperatures. So this is quite obvious, because if there is more humidity and more water, there should be less fire emissions. And this is shown here for Brazil. But temperatures are correlated, as we saw before, with fire emissions. Now we can move on and go further with our multivariable analysis. And now what we will do is try to understand which parameter is the most responsible for wildfire emissions and which has the most impact in terms of wildfire emissions, or which has the most negative impact in terms of wildfire emissions. So this is also done by the same library in Python, and is a tree. It's called a random tree. And with this, you can literally see which parameter is the most responsible. I think actually that in this graph, it's decorrelated, because soil moisture shows an important score, which doesn't make much sense if there is more wildfire emissions, but at least that's what our model calculated. And it's interesting to see that which parameter take importance in terms of fire emissions. So for example, winds don't have any importance, whereas soil moisture have importance, either negatively or positively correlated. And temperature has importance of 0.15, so it's not the most important between all, but it's also there. You can see that our model is quite accurate. So these are all tools that we can use for our analysis. And before we did it for French Guiana, and now we can see our random trees for each country. And well, we see that for Equator, it's quite accurate, but Colombia doesn't have a big accuracy because these models need to be redone, needs to be analyzed, and needs to be perfectionated to make sure that they generate the best models. But sometimes they fail at giving the best models, and we always have to be careful about this multivariable analysis and not overestimate or underestimate and overanalyze or underanalyze what we do. So I think this is it for the presentation, but the next steps would be from this analysis to use machine learning tools maybe and try to compute a model of wildfire emission predictions and try to compare this model with real data to see the efficiency of the model. And other steps that are taken in the research are also done in the political group that I didn't talk more about, but they're doing interesting research. And I know that now the research is also going into details about analyzing, for example, satellite images and try to use satellite images to analyze wildfire emissions. So there are a lot of ways that we can do it. And my part was only on the numerical data, the databases, and then the statistical analysis. So this is it for my presentation. And now maybe we can go to the code. I don't know if anybody has any question.
Is there any question? Okay, probably we can go to see the code and then we can discuss a little bit more about results.
Okay. I hope it was not too. I hope it was clear and not too.
It
too
was
much.
very good. Thank you very much, Leo. It was very
Okay.
clear, good. At least for me, because probably I am not a good sample because I am part of the research. But
Of course,
okay.
it helps. It helps.
Yeah.
Okay. So now I'm gonna show you the code. And for this, I shared a little Python notebook in Collaborate. I don't know if anybody of you has used this. It's on Google Drive, and you can share code and interact with it and work on the code. And I gave the link to Luis Carlos so he could share it with you, and everybody could be trying the code and see how it works. So this is the Amazon project. And I'll go step by step and you will see basically the same graphs as I showed you just before. So first we need to install two libraries, netcdf4, that is to install, that is to use Xarray, and CDS API, that is the API we need to download data. So in my case, I already downloaded the data, but if you want to download data from Copernicus, then you need to install these libraries, and then you need them to make what you want to do. So here, as in any projects in Python, we start by adding the libraries that we will use in the project, and if they're not there, we have to install them before and download them. So we have to import all the libraries, and as you can see, there are a lot of libraries involved in this project. I don't know how many. I'm not even sure that all the libraries are used, but at least they're all here. For example, OS is 2 times here, so I'll remove it. But yeah, there are a lot of libraries involved, and maybe some you already know, NumPy, Panda, that we don't use either. Xarray, Matplotlib is really important to do graphs. Let's move on. Now, as in any Google Collaborate, if you want to use the data that are also in the drive, you have to connect to your drive. So we do this little manipulation, and now you're connected to the drive. So to download the data, you need to correctly put the path of where the data are, and this path should be the same for you. Maybe you have to change some things because this is related to my computer and my drive, but it should be almost the same. And so now going into the code, this first cell that you can see is basically the coordinates of the Amazon rainforest for all the countries. So first we have the Amazon rainforest for Brazil, we have for Colombia, Guyana, and Ecuador. So as we wanted to cut our data set to surround only the Amazon rainforest, what we had to do was to see precisely where the Amazon was stopping in the country and delimit these areas. So of course they're not as precise because we have limited precision in the data set, as you will see later. And this can have an impact on the study because maybe we're not considering all the Amazon rainforest, or maybe we're considering a bit more than the Amazon rainforest, but they're pretty precise, to be honest. And we already defined them here. Then we define some parameters, and here is the interesting part where we finally download our data. So this is the first use of Xarray library. I don't know if anybody of you, maybe you already know Xarray, or maybe you don't. I don't know. Well,
Algunos sí tienen, some students have experience with Python and some libraries, but
okay.
not too much.
Okay. Well, Xarray is like any library to use data, and if you need to open your data set that you already downloaded, then you have to call it by this function, put your path, then put the name, and keep going with the code. And this is what it looks like. So here we have the data set for Brazil. I called it Big Data Brazil. It could be any name, but it's important to have good variables to always keep track of your code. And this is what a data set looks like. So as I told you before, we have informations about coordinates such as longitude and latitude here. And we see that our data set for Brazil goes from -72 in longitude to -46. So this is from west to east. And then in latitude, it's from 2 degrees north to -14 degrees south. So this is kind of a square that I'll show you later of data. Then we have parameter in terms of time, and it goes from 2003 to 2021 until the end of the year. And we have 1 point per day. So each day we have one data. We could also download each hour, but we did an analysis day by day. And now we have our proper data. So for each of these points in time and in space, we have information about wind speed, in the U direction, in the V direction. We have data about temperature, about precipitation, and about dew point temperature. And we could choose to add more parameters if we want to study other things, but here in these data sets, that's what we considered. Now with this data, data set, we can do some nice modeling, and as I showed you before the graph, see what it looks like for the 1st of January in 2023 in Brazil. This is what the wind speed looked like. Well, I don't know if it's interesting or not, but at least you have an idea of how to plot it by calling it like that. Then we can do the same with soil moisture. The architecture of the data set is basically the same, but instead of having informations in temperatures and in precipitation, we have information in terms of wind speed. No, sorry, not wind speed, of soil moisture, of course, and there are 2 layers, so it's probably the depth of the layers. And if we plot it, as you saw before the graph, we have a visualization point by point at that time. We can keep going, and this time I chose a data set called download, but this one is not used in the research, it's more just to show something that is nice. Okay, sorry. And this data set shows the mean sea level pressure, which we will not use in the research, but I thought that the graphic was pretty nice because we can see South America here and Colombia over here, and yeah, it's interesting. And with these data sets, instead of having point by point, day by day presentation, I chose to do a little animation to show you. If you run this code, then you will end up with an animation that shows you for each month the state of the mean level sea level pressure from 2003 to 2021. And you can do this for precipitation, for temperature, and see how it evolves. And we can see pretty clearly Colombia here, Ecuador, Peru, Brazil, and how it evolves. And for sure, we could see by season higher pressures in certain areas, and in other seasons lower pressure. So if you're interested by doing some little animations, you can just copy paste this code and put your own data, and it works. It takes a bit of time. So this was it for it. Now we can start our proper code and what I used really for the research. So as I told you, we need to cut our area in the Amazon rainforest area for each country. So I wrote a code that cuts. It's like, this is a function. This is how I define my function. This is the name of the function that is called cut ama area. And then the function will take will take some variables that it will work with to give you something at the end that you will define. So this is how you write a function. And for example, libraries in Python have a lot of functions included, but they don't have all the functions that you like, and you can create your own functions that can be way more powerful and make your life easier. And it's especially interesting when you need to repeat some task that you don't want to repeat writing the code. You can just write a function that will do what you want to do repeatedly, and it will do it for you, but you have to be precise. So this is my function that is used to cut the area into the Amazon rainforest area, as we defined the coordinates before at the beginning of the code. This is where it will go now. So these functions take data sets here. For example, the Brazil data sets, it takes the coordinates of the Brazil Amazonian rainforest, and it takes which variable we want to consider, for example, temperature or anything, and it will cut our data set into an area of Brazil Amazonian rainforest. So this is our Amazon rainforest in Brazil here, at least for the code. Now you can see how it cuts our area. And this was for temperature again. So instead of having the whole square, we have some kind of Amazon shape. And we hope it's precise enough so that it includes the Amazon for real. But I think it is. This is Brazil. And now now that we have our area that is cut, we go to the next function. And this function is used to do the graph concerning the tendencies when we compare a parameter such as temperature, let's say, to fire emissions. And this function takes into entry the country that we want to analyze, because we separate by each country, for example, Colombia or Brazil or Ecuador. Then it takes of course, the coordinates parameters to cut it into the right area. It takes the parameters we want to consider. So for example, temperature, or it could be relative humidity. It could be soil vegetation, soil moisture, sorry, I get confused. And then we can specify for what year we want it to be working. So if we want to focus from 2003 to 2008, we can say it. If we want to focus from 2008 to 2021, like we did in the study, we can also say it. So this is a function that I will use a lot. And how this function works, I can explain you a bit more in depth. The code maybe is that first it will open the data sets that we need. So if we gave it into entry temperature, then amazing, it will open the data sets in temperature. Then here, this function, as you can see here, I call my function that I used to, no, it's here, sorry. I call my function that I showed you before that I used to cut my area into the Amazon rainforest. So I can use a function in a function. And now from the data sets that I opened, I cut them into my good area of rainforest, and then I start to do some work. Here it's a special code that I did in case, maybe it's not the most optimal in terms of code, but in case our parameter is relative humidity, we have to do something a bit different because relative humidity is not given in the data set. So we have to calculate it ourselves. And so to do so, the same, we manage our data sets, but then to calculate the relative humidity, we need some functions that are given by physics and that we apply to our data sets. So the data sets can be, of course, operated, divided, multiplied, put into power or anything over the whole data set. And this is how we get results for relative humidity. And relative humidity is a function of temperature and dew point temperature, which are informations that we have in our data sets so we can use them. And once we open our data sets and we cut them into areas, we can start to plot them with a matplotlib library. We can also calculate tendencies, which I did here, if I'm not wrong, or maybe here, I did here. We can calculate the tendency, we can calculate the correlation and the p-value. And basically all this code is used to give this result here. Sorry, it's a bit zoomed. I cannot zoom out. Well, this is the graph, and I already showed you before, so I'm not going to explain you again. By the way, is there a break? I just realized. Luis Carlos.
Sorry, say again, please.
Is there a break for the?
No, just continue.
Okay, because I don't know if you had a break after. Okay.
No, just go ahead.
Okay. So I will continue. So now it's an example of how we use the function that I just described before, and this function is called core. It's called core parameter. This is the name of the function. That is a bit of a weird name. Maybe you should put better names for variables because I'm not the best at it. But as I told you, we say which country we want to analyze. So Colombia, we give the coordinates, we give the parameter, and we give some time. We can try together. I hope it's gonna work because otherwise I have problems. We can try, for example, for equator. I have to change each variable, and instead of trying temperature, we can try total precipitation from 2005 to, let's say, 2018, and let's see if it's gonna work. Hopefully it will, and it did not. Well, that's a bit sad. Maybe now it will work. Well, if it doesn't work, I will go back to Colombia.
We hope so.
Yeah, I hope so. It's loading. Maybe now it's working. Now my computer is not answering. Now it's coming. Okay, so instead of showing you temperature, I showed you total precipitation for different years, and we have a different curve, but it's a bit similar in some ways, and we can see some correlations and some p-values. So this is the use of this function, and now after that I have the same functions but for seasons and for months. So I'm not gonna repeat my explanations. Basically they work the same. They're a bit longer because there are more things to work in these functions, but they're built the same way and they operate the same way. And by the end of these functions that are pretty big, I have to say, maybe a bit too big, I could do it shorter, but it's what it is. You have again the same structure where we call a function, we give it to entry, we feed it with some information such as the country or the years, and at the end we have different graphs, this time showing seasons. And again we find again our graph with our tendencies and our repetitions in terms of seasons. And here again, well, here it's not well edited, I'm sorry for this, but what we can see is that, for example, in March there are almost no fire emissions from March to May in Colombia, as well as almost no temperature, but there are high fire emissions and higher temperatures in December, January, and February. So these are informations about seasons, and I don't know if you relate about it in your life, but in December, January, and February it should be a bit warmer, at least in the Amazonian Colombia. And in March and April and May it should be colder in general over the 15 years that we considered on this trend. Now we have the same function for months that is really the same, and that gives us a graph like this with a bit more variability this time, because we still have monthly and not seasonal averages, so it changes a bit, and the correlation goes usually a bit lower than the seasonal trends, because events are more seasonal, like warm temperature can bring a lot of wildfires, but maybe with 1 month difference. And this, we will see this difference, this little shift on this graph, but we wouldn't see it in the seasonal graph. That's why it's interesting to do both, to see the difference between seasonal events and monthly events. And again, we can see which month are, or when wildfire emission happen. So for example, in February, here in blue, we have high wildfire emissions, but also high temperature. And we see that both curves are kind of going around together. So when it's warm, there are high fire emissions, then it goes down from March to July, and then it goes up again for both curves. But of course, it's not as precise, and we have a good correlation, but it's not a correlation of 1, so it's not exactly correlated, which means there are other parameters. It's not just temperature, of course. Here, I did a little summary of some correlations. I'm not sure it's up to date anymore. And now we go to the multivariable analysis part. So I imported more libraries because we need sklearn, as I told you before. We need one called Seaborn, and I think that's it. So we import these libraries, and we import sub-libraries as well. And the first function that I defined was the one to do the grids that look like this. And so to do this function, again, I had to call all of the data sets here. And then with all these data sets, I had to make them work and correlate them between each other. And to do this, we use some training algorithm. I'm not an expert about this, and it's pretty complex. These libraries have a lot of tools and a lot of specificities. So you can play with these libraries, and by changing the parameters, it will make your functions better, and you will get better results or worse results. So you have to be careful with these parameters because they all have an important impact on the result. And these are these libraries also used to do machine learning. So you can do really, really powerful models and run really powerful algorithm. And here I train my data sets, and then I get some results that I'm not gonna go through the whole code, but that's the structure of it. And then here we have our model that we chose to train by linear regression, but there are other functions that you can call, such as the random tree that we will see later. And then you have to feed your model to your training, and then it will give you some predictions. And at the end, what you always have to do, which is here, is to plot it into nice graphs, which is shown here. But the model part was a bit above. So I already showed you the results here, and you can see the accuracy of each model. And well, unfortunately, the accuracy is not always great. So here it gives us an accuracy model score and the absolute error, I think, of 0.33. So it means it's not the best score. And maybe if I change the parameters above, I would get better score. and I would get better answers. So this means I shouldn't take it as it is, and I should improve it. I didn't go as far, unfortunately, into the research. Now this is the plot for Colombia. This is the plot for Ecuador, and this is the plot for French Guiana. Now we go into the random tree part, and again I define a function that is almost the same as before because we use the same library, but at the end we change some parameters, and instead of training our model with linear regression, we train our model. Let me find where is it. We train our model with random tree, I think. I cannot find it now, but it's here. Random forest classifier. That is, if I'm not mistaken, that is the name of our algorithm. And again, we have to specify some numbers to train it. And maybe the code seems to be a lot of information. Maybe it's losing a bit, but all these things you can find so easily on the internet, and there are good documentation that explain you how you can get the best method to use and how you can get the best results for your data. So I don't know all these libraries and all these functions, but I know that if I check, then I can find really nice examples, and then when I apply them to my data, I also can have tools to check if it's actually working, and we can add some layers to this analysis. So that's why it's interesting, but it's a bit confusing. And at the end, we get these trees. And this is it for the coding part. I don't know if you have questions about the code or about something else, and if you want to try it.
Leo, thank you very much for this very nice presentation. It has very clear, very useful, and of course it is new for us, and for many of us is something that is that's been done now, and this is an ongoing research. Um, so I'm very happy you have been part of this work, and I'm happy you came to Colombia, and I hope you return to Colombia again and continue working in this
I
field.
hope so. I hope so very much.
Yeah, it was very
I
nice.
I hope you enjoyed the presentation and it was clear enough. In case you have questions,
Yes,
don't hesitate, of course.
yes. Is there any question? Even if you want, you can ask in Spanish, as you prefer. Pueden preguntar en español si quieren. Um, for the moment, I have a question. Leo, can you give us share your experience working with the Google Colab and Spider? Is it really different, or is there any advantage, or would you prefer to only use Spider or any other platform than
Of
Google Colab?
course. Well, I think,
Your
on my
experience.
experience, to code, Spider is nice when you have a big project and you want to run a long code. But I use Python Notebook, which is basically the same as Google Colab. It's like the same because it's quite nice because you can do your code step by step, and it's much easier to understand and to not get lost into the code and to check if you have errors. And also with Colab, you can share it, so that's really convenient. But Spider is better for longer projects because it's not as heavy, and you can run the whole code at once.
Yeah. Hmm. Yeah, and did you try this? In Google Colab there is um, support you have from Google that you can use more CPUs, more memory, and have you tried
I
that?
wait, I think it's here. I haven't tried, but like here you can use more properties and you can have better efficiency. But I've never tried. No, I should try. But it's quite fast usually.
Yeah,
The code runs well. Sometimes it's a bit heavy because as it's on internet, sometimes it bugs a bit, it lags, but it's good.
mm, yeah.
But I've never.
So yeah, and what is your feeling about CAMS, this Copernicus database? Do you think we can really trust on this database? Is it good? And what would be your recommendation to try to test it or to improve it, to improve the way we use it?
Well, I'm not a specialist in terms of environmental data, but I found it super nice, and it's quite easy to use. Like for real, it's quite easy to use, and you can explore it extensively. But maybe it would be interesting to compare it with other data sets, like because this is just with CAMs, but maybe we could use database from another agency, for example, from the US or from Colombia and Brazil and whatever database, and try to compare, because it's always better to have more data than fewer. But I would say it's pretty good, because I think from what I read, the database that we used is the CAMS reanalysis 5 or something like this, that was released recently, and they did some work on their data to give the most precise data. So I guess it's one of the most accurate we can get for free, like as easily as that for research.
Yeah. Well, unfortunately, we don't have experience with other database, but will be interesting to test, for example, information from the States. The thing is that it is easier to work with this Copernicus information as you show. It's very easy. Okay, we have one comment in the chat and one person who is raising the hand. It is Gabriela. So I guess we give the word to Gabriela, and then we answer the question in the chat. Gabriela, please, can you open your microphone?
Yes, hi. Thank you very much, Leo, for your presentation, and for Luis. I was wondering if this research is going to be presented somewhere. Is there going to be any scientific article? Because it's really interesting and important to be shared with more people, I think.
Well, I think so. Maybe we'll ask to Luis Carlos, because I'm not sure where it is at now. Like I'm not as involved as I was. I think the point is like right now writing an article and share it. Am I
Yes,
right?
we are working on a paper, a research paper. As Gabriela mentioned, it is very interesting. Actually, this study trying to find a relation between meteorology and emissions and policy is quite interesting. So we are working on this research. Actually, I would like to thank to all the team, because it is we are not only Leo and me. We have Alejandro Casallas, Eli, we have Natalia, we have Camila, we have a very large group, Ricardo. So I hope, I don't know, probably we will finish this paper at the middle of the year, and we will submit it probably starting August or September. I hope it will be probably published at the end of the year or probably at the beginning of the next year. And of course, Leo, you are welcome to participate and to continue working with us in this paper.
Nice, thank you.
Yeah. There is
Yeah.
a,
Also, sorry, go on.
no, say please go ahead.
No, also is that my part, like what I showed you, is what I have done with Alejandro, but the others are doing other work on the politic part, and now there is more as well on the satellite images. So there are a lot of things to compile and to compare and to understand. So it's really much more than what I showed you. It's big.
Yeah, it is a big work, and we hope we can publish and share it with everybody. So there is a question in the chat, Leo. Can you
Yeah,
read?
yeah.
Mhm.
Um, Hi, Carol. Yeah, to answer your questions, if we consider using more variables, actually we did. And at the beginning, we used less variables. I think we only used temperature, precipitation, and wind speeds. And then we added soil moisture and I didn't show you, but I downloaded recently leaf coverage, which is another parameter. But I don't know if I implemented it in the code yet. But definitely, I think it's a really big point to add more parameters. But it's always tricky because you have to be careful about not adding too many parameters first, because then it gets more complicated and you might get lost in all the parameters. And also, you don't want to over analyze. That's also a thing that you have to be careful when you do this statistical analysis, is that if you add some parameters that seem to have a correlation, it doesn't mean that they actually have a role in wildfires. But definitely it would be interesting to add other parameters. Definitely.
Yeah. There is another question here from Naisla. It's in Spanish. ¿Cuáles son los criterios al momento de seleccionar los países a estudiar?
I hope you don't mind if I answer
the countries. How
in
did we
English.
choose the countries?
To choose the countries,
Yes.
well, I think we chose them, as I said at the beginning, because they showed interesting patterns. Maybe I can show you, I'll show you again my presentation over here. If you remember this slide, they present interesting patterns. So first, Brazil was kind of clear that we would study, because it's the biggest country and it's the most responsible for wildfires in the Amazon and maybe in the world. So we had to include it in our research, and also the fires are going up. So it's important to have a view on this one. Then we chose Colombia because we're in Colombia, and I think it made sense for everybody. And also it's the second country that has maybe the highest increase in terms of CO2 emissions for wildfires in the Amazon. So it was interesting to include it. Then we chose French Guiana, that is here, because first the tendency is decreasing, it's going down, but not as clearly. You can see there is a big variability between each year. And it's interesting because French Guiana is part of France in Europe. So we can, in terms of policies at least, not in terms of climate, but in terms of policies, we can assume that regulations are different maybe than other countries such as Latin American countries. And so it's a challenge as well to try to see how a European country deals with the rainforests, because European countries don't have rainforests, at least just France in this little part. So that was also one of the key. And finally, we studied equator, because maybe I'm wrong, but I think that somebody was in equator, and then it was easier to study this case, as well as we chose it because it was also decreasing, and we wanted another country that had a decreasing tendency. So I think these were the reasons. And if I keep going with the questions, if I understand well, is what is the good time to study this?
Yes, or if we could, probably it is if we could choose a time period where we could study, maybe to improve the results.
That's also really interesting, because when we study climate trends, like climate is at the end, even if it evolves really fast, it's a long scale phenomena, and it's on longer time period. So it's better to study it on longer times. And we chose to start from 2008. And to be honest with you, I'm not sure why. Alejandro told me to start in 2008, but my data that I have here could start in 2003. And there are some data sets in CAMS that have data from 1950, maybe not the same precision, and it's not a reanalysis, or at least not the fifth one. But you can go way further in time. But 2008 seemed pretty recent, but you still have a view over the 15 last years. And now we could also include the 2022 and the beginning of 2023, because I think the data are available. Like, I started this project 7 months ago, so there were less data, and I just took until 2021, but we could go as far as of now. Of course, it would be more precise and interesting. And that's also interesting. The question about the el material vegetal, and that's a thing that I didn't show in my code, but there is one data set. You can also download data sets that show different kinds of vegetation, and you have high leaf vegetations, so probably high trees with big leaves, and you have low cover vegetations. You can also download data sets that will show forests or marshlands or other types of vegetations. And this would definitely be a parameter that we should include in the analysis, because definitely, depending on the type of vegetation, you maybe don't have the same wildfire regime and the same the same analysis. So yeah, I think it would be a parameter to consider.
Okay, one last comment, Leo. Our students are going to prepare a project. This is the final project for the course. And probably
Okay.
some students will work with your code. Probably they will play with the code and try to change some things. So if possible, could you be able or available to help them if they have any question?
Yeah, of course, of course. Do you want the link? Should I send it, or you have it, or?
Not yet, but you can send it to the
Okay.
via WhatsApp or to my email, and
Okay.
I will send it to the students.
Okay. No, but of course I am available for any question or any help. My pleasure. I would help
Oh, thank you very much. And
if
again,
I can.
yeah, thank you. And it is very interesting. We are learning a lot about this. It's new for us also, trying to find a good way to analyze the information. Thank you, Leo, again. And I hope you can return soon to Colombia, and probably we work together or continue working in these kind of projects, or probably new projects. And
I hope so. I really want to return to Colombia. Thank you for the invitation.
yeah. Okay, so we finished here. We are going to finish. Thank you, Leo, again, and I hope to see you soon.
Thank you. See you soon. Good weekend. Goodbye.
Okay, bye bye. Okay,
Bye.
thank you. Bye bye.